Hello, my name is Man Chow, or Kenneth Chow, you can call me. This topic I'm going to talk about today is the video number 18 of my series, Quantum Gravity series, video 18. The topic today is unification of quantum mechanics with general relativity. I've talked about this subject already in my video 7, which was in October 2021. In that video, I showed that the equation of motion of a material point in a gravitational field is equivalent to the equation of a particle in quantum mechanics, which is the Schrodinger equation. Schrodinger, S-C-H-R-O-D-I-N-G-E-R, the Schrodinger equation. In that, both the equation of motion of a material point in a gravitational field under the general relativity and the motion of the particle under the Schrodinger equation are both wave equations. And further research since my video 7, that's about 1 year and 5 months ago, I have now been able to give a strict proof instead of just to demonstrate that both equations are wave equations. I can now give a strict proof. A strict proof that's similar to my strict proof of that the gravitational force is equivalent to the electromagnetic force under the Coulomb's law, like in my video 5, and also that to demonstrate that the Weyl theorem is equivalent to the Oppenheimer-Volkoff Equation, like in my video 16. Firstly, I have proved that in this video it also involves the Oppenheimer-Volkoff Equation, which is a derivation from the theory of general relativity. In this video, I'm going to prove that this Oppenheimer-Volkoff equation is equivalent to the Schrodinger equation, the time-independent Schrodinger equation, which is a derivation from the Schrodinger equation of the quantum mechanics. First of all, I have to give some history about this Oppenheimer-Volkoff equation. The equation was derived by J.R. Oppenheimer and S. Snyder, his colleague, in 1939. That's about 84 years ago. This is actually the very first modern, I have to emphasize the word modern, paper on black holes. Because the more ancient paper on black holes has been by Pierre Laplace in the 19th century, and also given by the English astronomer William Herschel in the late 18th century. So this is the first modern, I have to emphasize the word modern again, modern paper on black holes, the first given by Oppenheimer and Snyder in 1939. After Oppenheimer gave this derived this equation, it was further developed. The theory of black holes was further developed by David Finkelton in 1958 in UK, and also by Martin Kruskal in about 1960, which is a maximal extension of the Schwarzschild geometry in USA. And then it was also further developed by Roger Penrose and Stephen Hawking in the late 1960s. The theory they proposed was the black holes singularities beyond space-time. The Oppenheimer-Volkoff equation was derived by Oppenheimer when he was the director of the Institute for Advanced Studies in Princeton, USA, at the time when Albert Einstein was a professor there. He utilized the Einstein's theory of general relativity. It was not clear whether he wanted to convince Einstein that black holes are physically real entities, which could be derived from the Einstein equations. You have to remember that Einstein rejected black holes as physically real entities, but he later converted to a believer during the later years of his life. Einstein died in 1955. Now I have to give a brief outline of the derivation from the equations of general relativity to the Oppenheimer-Volkoff equation. I have to bridge the process, so this video may not take so long. You have to firstly have the conservation equation, the divergence of the gradient of the divergence of gradient of the Laplacian of the energy tensor T mu nu, contravariant tensor, can be written as log c square plus p, which represents the pressure, divided by 2a, where a is a function of the distance of r. This r represents the distance to the center of mass of the system, multiplied by g mu nu, which is a contravariant tensor, and del a in respect of mu, plus g mu nu again, del p is equal to 0. Log is density of the mass, p is the pressure of the mass, a is the function of r, which is the distance to the center of mass of the system. C square is the light speed square. Secondly, multiply the whole equation, both left side and right side, by g mu sigma, and simplify the equation then becomes log c squared plus p divided by 2a del times del a to in respect of sigma plus del p in respect of sigma is equal to 0. And then we have the third process. For sigma is equal to 0, 2, or 3, the above equation is trivial. Trivial means it's all equal to 0, just 0, remains 0. And that is to say, the p is independent of time, t. But for sigma is equal to 1, the equation is non-trivial, and it becomes a pi divided by a is equal to minus 2 pi p pi divided by log c squared plus p pi, where prime denotes the differentiate something divided in respect of r, the distance to the center of the center of mass. This is a differential equation in terms of log. Now becomes a differential equation in terms of log r and PR, which AR must satisfy in a hydrostatic equilibrium. This is actually the equation general relativity by Albert Einstein to describe the equation of hydrostatic equilibrium of Euler, which is who's a mathematician of the Switzerland in the 18th century. Now the equation then implies an equation of state P is equal to P sigma. That is to say, P equal P in terms of sigma. This is the first equation of stellar structure, and is written as dmr divided by dr is equal to 4 pi r squared log times log r. Whenever I say the bracket r, that means this is the log in terms of r, a function of log in terms of r. The sources of this is from General Relativity, the book by Werner Israel and others of the Hebrew University of the Tel Aviv, with chapter 12, page 292 to 295. The second equation of stellar structure, also known as the Oppenheimer-Volkoff Equation, the second equation of stellar structure,